Okay. First slide. 1 second. All right. Okay, so this is a brief overview of what we're going to talk about, and I'm not going to go through this. Just going to give you a heads up that we're actually going to talk about a couple technologies over a range of wavebands. So we'll go to the next slide, please. So if you were to do a survey or census of the electromagnetic spectrum as an astrophysicist, this is what you might find. At the low end, there's is there a pointer here? I don't know how to use it. Is that it? At the low end, you have the cosmic microwave background, the cosmic infrared background, cosmic optical background, and the X-ray background. And most of the photons are in this low end, and they are very interesting in terms of how, controlling the. They're interesting for several reasons. So the next slide, please. So the far infrared is used for a variety of reasons, which are listed there, and I'll let you read that. But perhaps more important to me, from my interest, is how does initial star formation and how do the early heavy elements come about? Under what conditions were the heavy elements created? And what are the processes in AGNs? Okay, and more importantly are the cosmological. It's a wonderful probe of cosmology because it lets us look back to the earliest times. Next slide, please. So here's a picture, and I want to step to the next slide and just look at how the sky, this is the galactic center, how it looks in different wavebands going from there, and one more. And those are largely foregrounds. We don't look in the galactic center when we can, but they're largely foregrounds for a lot of things we're interested in doing. And in looking at the Big Bang, it was originally a very hot initial conditions, and the measured fluctuations are consistent with a very simple model. It's called lambda CDM, which I don't know if you are aware. But anyway, that's what it's called. Which a universe was composed primarily of dark energy and dark matter. The CMB photons observed today were from the surface elapsed scattering, and when the early universe transitioned from being optically thick plasma to being transparent. And during that period, the information about the density and the composition of the universe is encoded in that plasma. Okay, next slide, please. This is a recent map made by the Planck satellite. And what's of more interest now, this is in temperature, and Planck made a full sky survey of the sky. Are these images here, which is the polarization, that's the hot and cold spots in so-called E mode, which is jargon for something that looks like an E vector, it's radially inward, and they've been detected, okay? And in this picture, they're consistent with this lambda CDM model, but perhaps, and that's induced by scattering off the compton scattering off of warm and cold, dense and underdense regions of the early universe. But there's another symmetry which one could look for, and that would be a B mode or a curl-like symmetry in it under certain cosmologies would be present. So go to the next slide, please. In addition to that, we can pretend that the CMB fluctuations that we map are our standard candle, and we can consider the lensing from material between that last scattering surface and between the observed sky today, and we can try and undo that. And that allows us, that delensing process is a very interesting prospect. The lensing creates correlations or deflections in the radiation on degree scales today. That light, studying the properties of the power spectrum allow us to look for essentially allows you to do high energy particle physics, set constraints on neutrinos and other processes that the matter density and dark matter. The next slide, please. Okay, so this is a collection of the most current data. If your favorite experiment is not there, I apologize. In the interest of having it in a finite amount. But the upper one is the Planck data. These are the temperature fluctuations. This essentially, the axis here is like 1 over angle. This is the largest angles on the sky, and that's the smallest. And this is the E mode, this radially type symmetry in polarization. This is unpolarized light. And what we're interested in now is to find out if this B mode type behavior is there, and that will tell us about the earliest times of inflation. In effect, you're using the properties of the light to serve as a gravity wave detector on the larger scales. Next slide, please. So you could ask, how do you do all these measurements? And to be honest, it's hard. And these detectors, this particular detector, this is the ACT from the ACT-POL collaboration. This is their telescope. There's a cryostat here. These detectors run at 100 millikelvin, and they look out into this particular telescope is in the Atacama Desert. If you were to fly this from a balloon, there'd be other complications if you were to fly it from space. But the bottom line is it's a TEAS-based detector array, polarization-sensitive polarimeter with multiple elements. And it's running at 100 millikelvin, and somehow you need to go from 100 millikelvin to a more warmer temperature, in the case of this telescope, to 300 Kelvin, without loading the detector or spoiling its noise properties. And so there's all kinds of little engineering problems that arise in that context. And let's go to the next slide. So we want to think about, I'm not going to talk about TS detectors and that. I'm going to talk about some of the minutia of how do you do that. And metamaterials in general are just engineered materials or tailored materials that have properties that are not readily found in nature. And you could say, well, you don't find Teflon in nature, so why is Teflon, one of the ones I put there? In general, like the Teflon is actually has a controlled pore size, and that's why I've included it. I kind of use there are also two-dimensional metamaterials, which are like, you can imagine metal little printed circuit things that are printed, and we're not going to talk about those. These materials fall into the category you control by controlling their properties. Either typically you try and have them do one or more enhance one or more properties. Maybe you want to make it lighter. Maybe you want to make it have a certain optical property. Maybe you want to have it have certain mechanical properties. And this is important if you're trying to cool something down. If you have a large silicon lens or something like that, you might not want it to break. And some of them are the various techniques that are made, like these are made by chemical, essentially etching. This is made by laser-assisted etching. This is done by DRE, and this is by similar micromachining processes. Some of these, like these nanoparticles, are made by essentially just controlling the chemistry in a way to generate particles of a certain size. Next slide, please. Okay, so one of the problems which we'd like to solve is we want to have many detectors. We want to make a very large field of view instrument, and we want to have many detectors looking at the sky simultaneously. And due to we all have computers, large chunks of silicon are readily available, more or less industrially. You can get a 30-centimeter piece of silicon, and that's a reasonable material to make a lens out of in the far infrared. And the kind of traditional way of making an AR coating is you essentially glue a material or layers of material and make a composite material. And next slide, please. The problem with that is that the stresses that are built up in that tend to pull chunks of material out of the lens and cause other kinds of issues. It also can deform the very shape of the lens, and that's bad. So what we looked at here is an alternative solution. We make sub-wavelength features to realize the multi-layer coating. And at University of Michigan, they essentially built a gantry. It's a 3-axis dicing saw mounted on a gantry with 1 mil accuracy to realize these kind of structures. And you could say, well, that's the other thing I didn't mention. In making a millimeter wave coating, like the CMB is peaked around 150 gigahertz, so it's kind of millimeter wave radiation. One of the problems is the coating you would want, or the control structure for controlling reflections is actually relatively thick. And that is another challenge, whereas if you went to the optical or something, you'd be like, okay, I can live with that. Okay, so the strengths of doing this are it gives you precision control over the index of refraction, an ability to create multiple layers over a large area, and others that are there. But in particular, this volumetric metamaterials, they can achieve a higher bandwidth than their planar counterparts. You can imagine doing the same thing by stacking, and you'll find that in the end, you're going to need a lot of layers to do that. So this is a very efficient approach to carrying this out. Next slide, please. Okay, so here's a simple example of the upper is kind of showing the basic idea. This is a cartoon, it isn't what we actually do. But you could imagine drilling holes or having rods and attaching that layer to a bulk material and have another material. And that's really good in this situation because if we're going to cool something from room temperature to 100 millikelvin, or even 4 Kelvin, to be fair, we're not going to 100 millikelvin, 4 Kelvin, 3 Kelvin, something like that. This is all the same materials, so you're not going to have all kinds of, there's not going to be a lot of stress in the structure. Next slide, please. And so you can kind of, to zeroth order, you can just think about it as a function of the filling fraction. There's some effective dielectric constant that you're achieving. Okay, next slide. So you can, by playing with that, the filling fraction, you can realize any value you want. Now, if the pitch between the various objects becomes becomes too large, you'll diffract. You could look at that as a feature or a problem, depending on how you view it, but it is a reality. Because it's essentially, as you go to really high wavelengths, the material is going to scatter light, which could help you or hurt you, depending how you did the rest of your optical design. But you need to keep it in mind what's going to happen out of the band. A lot of the structures we make actually which were made at Michigan and designed, the designs we're exploring, they have a very large fractional bandwidth they operate over. So you start with a big 30 centimeter piece of silicon. Next slide, please. And here's a graduate student. He's diligently operating the machine, which he designed and built. It's controlled to a fraction of a Kelvin in the room to get the tolerance he wants. And it's essentially going through and cutting on this after the shape of the lens has been formed. Next slide, please. And here are pictures of the final finished lens. It's incredibly, it holds our tolerance, the uniformity of the material. Both you have to cut it uniformly on X and Y, otherwise it'll become birefringent. So you could use that to your advantage if you so wanted to make something but in our case, for this particular application, we do not want it to be, have a birefringence or biattenuance. Okay, next slide, please. And here is the actual end part compared with theory and model. It works out very well. These lenses have been deployed and have been used in the field now at this point. They're mechanically robust, and you just don't want people picking them up and playing with them, but they handle transport to the telescope fine, and they are useful once they're mounted. Next slide, please. This is a really nice photograph of a demonstration of a 5-layer coating, and it's the band. It operates over a 5-to-1 band. It's a kind of approximating a little cone over the type thing. Next slide, please. Here's another approach we tried a few years ago, and we've kind of revisited it. This is one that's larger. We actually have made much smaller ones now for more like 20 micron work. But it's essentially a DRE, it's essentially silicon micromachined hex of a finite length. And you can see at really long wavelengths, it's acting very well as a homogeneous dielectric. And as you go higher in frequency, there's some dispersion. And if you go high enough, you start seeing resonances in the structure. But we'd normally use it kind of in this range down here. And next slide, please. If you take that into account in the design of the next layer, you can, it works out fine. So another structure of interest where metamaterials can maybe help you out is if you have something that's really cold and you want to put it next to something that isn't so cold and you don't want to have a large thermal load on the cryostat. For systems with waveguides in them, this is an important consideration. Back when I was in graduate school, you'd take a piece of stainless steel and you'd put the flanges on it, and the loss in that guide tended to be the dominant error in making in using receivers of that type. Calibrating that out was for noise measurements was tricky, even if you plate the inside. You ended up having a longer length than you'd want to have. And so with this approach, essentially you could imagine two waveguide flanges that come very close together. If you work with waveguides, what I just said would scare you, because if you know a little tiny gap, it leaks out of it. So what you do to get around that is you make, this is the two flanges coming together. You put a pattern of little pillars, and that pattern essentially lets light go, doesn't let light go radially away from the waveguide, which is in the center. The waveguide's running along this axis. And if you think about it as a pattern of mirrors, you can mirror all the ones above, and it makes an infinite array that way. And in the end, you have essentially, if you mirror all the ones down, you have going below. And what you've done is you've replaced the walls of the waveguide in this house of mirrors by these pillars, which do not let light go laterally, and the waveguide ends up being a defect. This works really well. And Jeffrey Heftzler, I believe at UVA, made a structure along this line in quite some time ago in 2-to-1 aspect ratio guide. And the thing that's special about this one, this particular design, is that it actually allows you to have both polarizations without loading either one. And you can, and if you want them to touch, you allow them to touch, it works with lower loss than the other type of, than a traditional flange would work. You can use it in a split block. We actually we've micro-machined some of these out of silicon, this pattern into the interface layers, and we built circuits inside in the gaps that exist in between. So it's a very nice packaging solution if you want waveguide structures very close to microstrip or other transmission line structures. Next slide, please. And this shows, for this particular design, and these are the pieces that were tested. This shows the response of the stop band. Next slide, please. But that's a narrow band because it's only one set of scale that's setting the band, but you can repeat that and do that multiple times, and you can do a larger one. This was done by an undergrad student as a project, and this is a scale model for a package that was built at 300 gigahertz, where, so bolometers, essentially any light that hits them, they're going to absorb, and that's a problem. So a problem when you're building bolometers on the low side, in a waveguide-mounted bolometer, the low side is pretty well protected because it has a waveguide cutoff. All the light is reflected away. But on the high side, where you're multi-moded, you actually need to worry about what's happening over a huge bandwidth because the blue leak light that gets in can degrade the performance of your detector. And we've also made variants of this where we've, instead of doing it reflectively, but if you're cold enough, and you can also do this with lossy media incorporated in the design, and that works well also. Next slide, please. Okay. So one last thing I want to talk about is the use of metamaterials and absorptive structures. And so if you're going to build an absorber, it needs to be compatible with what you're going to do. Like it has to have the right heat capacity and electrical properties so it actually absorbs lights. And as you go over that band I showed you at the beginning, kind of from the, the 10 centimeters to 20 microns is probably the range I had highlighted in green, something like that. A reasonable solution is you say, oh, I'm just going to make a thin film resistor. But if you go and do that, and you say, well, how much gold is that, or whatever you pick is your favorite metal, you're going to find out it's pretty thin. And you may find out that it isn't very stable, because the target impedance you're going to want to make out of the type of materials you can use. So there's one other thing. In saying this, I'm saying I'm not going to make a resistor to make a cell phone. Okay, I'm going to make a resistor that I'm going to cool to 100 millikelvin. I don't want its value at room temperature to be significantly different than it is cold. I want it to be a disordered alloy. And so it turns out that that's actually hard to do. So largely what we do is there are values you can hit that are stable and have all these nice properties, and you pattern the materials to do that, but then you're kind of introducing diffraction into the problem. But patterning in itself is a two-dimensional metamaterial. You can think of it that way. These volumetric things, it turns out they have a nice property that along their axis, you think about it where they're kind of adiabatically coupling to the light, they actually are very effective. So they do have a place. I wouldn't say they're used everywhere, but they're places where they actually make sense. Okay, and in particular, they're useful for calibration targets and calibration standards because they're calculable, they're insensitive to their fabrication properties, and you can, I'll show you one in a minute, where you can understand their temperature profile very, very well. And they're also useful in glint reduction and baffling because you can make them in a way where they're insensitive to how you make them and they still work. And also for passive cooling in some cases. Okay, next slide, please. So here's an example of a calibrator that was made in my lab by a student who, he made a calibration standard. This stretch here has been pulled to emphasize what's going on. Because to be honest, if you looked at this particular one with your eye, you wouldn't see hardly anything at all. You'd have to look pretty hard to tell. So the stretch has been changed here so you can see. So he made this calibration standard, and it turns out he came back and he said, well, this isn't black enough. And so he was interested in making this. So we made these little targets. These are all flats, and we look at the various materials. And these are conversion coatings on these lower ones. And that's a typical black paint that you might use in the far infrared, not in the far infrared, in the optical. Is where it's normally used. It's Z306. And so anyway, this is the standard thing that you would normally get if you went to a company and bought a calibration standard for your FTS. That's what they would give you. In fact, one of those is that, and one of those lines. And this is what the structure was able to achieve. And this is about a factor of 50 difference in performance. But the main reason why it was done was not because of that. That isn't why it was done. Because to be honest, we want to make it blacker. We know how to make it blacker than this. It was done because in his application, he wanted to run this and he wanted to know the temperature gradient across this, and he wanted it to be very small. And it turns out this was done with a metal backing behind it. So, tailoring the structure shape is another example of how it can really help you if you think through the physics of what's going on. Next slide, please. Okay. This is kind of an interesting structure here. The reflection that we wanted, this had more to do with making something compact. This is a micromachined silicon object that has been coated. And it needed to slip in behind a detector and terminate light that would have otherwise been reflected. And it needed to fit in a very small region, but it didn't need to be incredibly black. It needed to be greater blackness and absorptance higher than 0.9. And it's probably like at the low end of the band, it's probably like not 0.95, and in the optical, it actually is quite good. But where it's actually being used is around 0.95 or better. So that's another place where you can play that kind of game. And there, in this case, given the bandwidth that was required, a traditional design, it would have required multiple layers to do this. And it's easier to make this than the other structure. This is a piece of carbon nanotube. and been pulled out and photographed. But if you think about it, it's kind of the inspiration for this part. They're essentially these long needles, the photons come in and they're slowly being absorbed as they go down along the length. Next slide, please. And so for carbon nanotubes, which are mostly used in my lab more in the infrared, in the optical, but they actually, if you look at them, we've had some samples we've made that are quite long, and we can kind of make things of that length or less, but that is kind of the maximum length I can imagine making. Probably more like 200 is better. But if you play with essentially the filling fraction of the density of the material, you can see that it actually is a reasonable material in the, down to about a terahertz. Next slide, please. And so one place you can use that behavior is if you can use it for passive cooling. So these are various materials, and I'm not going to read them all, but the ones of particular interest are up here, and these are the carbon nanotubes. And they are pretty effective at the one problem, or one challenge is, so we do a lot of superconducting stuff, and the substrate material, the way they're bonded down is magnetic, and we don't really like some of those materials, so we actually haven't integrated them into our sensors, but for warmer sensors, where it's less of a problem, they're fine. I am not confident I would use them below the temperatures I plotted here for. The other thing is they can act as a getter, I guess is my other concern with them. But they do have a place. They're incredibly, especially if you pattern the material underneath them, kind of playing the same game that was played with the metal absorber I played, you can make something incredibly black with them. Okay, next slide. So our funding for this research, this is not the main thrust of what we do. These are things where we filled in holes in various projects. So, but the work we're doing, which is more directed towards doing astrophysics and studying cosmology, is funded by a variety of sources, and they're listed here. Next slide, please. And so just summarize for the anti-reflection coatings, the broadband emitter material systems, they're fairly advanced and they work quite well, quite happy with the way technology potential enables compact terahertz imagers, spectrometers, planetary remote sensing. The use of silicon, you have to think a little bit about. Silicon is not a dielectric, it's actually a semiconductor. So you need to use very good material, or you need to adequately address what other radiation is impinging upon the lens. So that's something to keep in mind. It's a feature. In our case, we run so cold it doesn't matter because they freeze out. So, but we have contemplated, and we are using some of these lenses warm, and I won't read the other ones. Okay, next slide. And we have some other plans of how to advance these technologies for uses, mostly in the astrophysical context. Thank you.